Hey everybody, this is Professor Ross, and in this video we're going to be talking about inference for the regression slope value with a theory-based approach. Let's take a look at some notes here. So once again, we want to talk about how we can do inference and especially look at hypothesis testing and confidence intervals. And we want to do that for the regression slope. Last video, we talked about a simulation-based approach, and here we talk about a theory-based approach. Our key learning objective is to use the logic of statistical decision-making, thinking about how we can use that logic to make a decision about a claim about a slope or to find out what we believe about a slope out in the population. As usual, we've contrasted simulation versus theory-based. Simulation uses shuffling to simulate pairing a response with an explanatory value under the assumption that the null hypothesis is true. We need a lot of computing power to do that. That's why we haven't always used simulation-based approaches, because we haven't always had computers available and handy that we could do that with. Nowadays, they're fairly ubiquitous. That's a great approach, and you can use it anytime you want to do inference with a slope. The theory-based approach historically has been used when we didn't have computing power for simulation. It's also a great approach when we meet the validity conditions, often related to having a sample size that's big enough. Here we'll find that these validity conditions are hard, to a certain degree, hard to even determine whether they hold if we have a very small sample size. So when we have very large sample sizes, that's often a chance for us to use a theory-based approach. The computing power can get bogged down with very large samples, and a theory-based approach can help there. The theory-based approach does use the central limit theorem, the same theorem we've used all along, and it predicts certain things about the way the null distribution would turn out. That's essentially what it's doing to help us obtain a p-value, and then we can make a judgment based on our p-value. The validity conditions for two quantitative variables, when we're trying to decide if we can do a theory-based approach um, with two quantitative variables for a slope, are a little bit more complicated. So we're going to spend a little bit of time in this video thinking about these. Our previous ones have been things like just check that you have 10 successes, 10 failures, or at least 20 in each group and little skew, those kinds of things. The ones for regression are much more visual. So we want to examine a scatter plot and talk about and take a look and see, do we have these things showing up in our scatter plot? And we want to decide if there are three things happening from our scatter plot. Do we have a general linear trend? Now, we've already noted before, if you're going to do anything with correlation coefficient, you already want to have established from a scatter plot that you have a general linear trend. Even before you calculate a regression equation, you want to do this. So this is a real baseline kind of validity condition that we should already be checking anyway. Next, we want to look for approximately the same distribution of points above and below the regression line. Some rough symmetry about the regression line, similar looking spread and distribution of data above and below the line. And then lastly, we want to make sure the variability of points around the regression line, should be similar regardless of the value of the explanatory variable. What that's saying is that if we've got a sorry, my pen is having some issues here. Here we go. If we've got our data and we've got our regression line, we don't want to see any kind of trumpeting effect where the data is close on one end and then starts spreading out toward the other end of the line. So as we travel down the line, we don't want to see the data really tightly packed in one place and then much more spread out. That's a red flag for us. Or vice versa, we could have real widespread at this end here, and then squeezing down tighter at the other end. That is once again a red flag for us. So we got to check all three of those conditions, and if those seem to be okay, then we can feel okay about doing a theory-based approach. We tend to err on the side of believing that we've met these conditions unless we have really clear evidence otherwise. What are we saying? In general, we like to try to do linear regression if we can. and we want to feel like a theory-based approach is okay. If there are some really clear red flags with any one of these three, it's clearly not linear. Pardon me. Or we've got a distribution of points that's different above or below the line, or we get this trumpeting kind of thing, then we might feel like, hey, we shouldn't do theory-based. And then, of course, you can always do simulation-based, which is a great option when you don't meet the validity conditions. Let's try this out. I'm going to give you a picture, and I'm going to encourage you to pause the video and see if you can make a decision about our three validity conditions based on the scatter plot. So I'm going to encourage you to try that out for the scatter plot. Here, we have a couple of problems with this data set. The first one may or may not be met. It looks like it might not be too bad of a linear trend here, but if you look again, it looks like we might have more clearly some kind of curve going on. And so we may not meet that condition. That one may not be too bad, but approximately the same distribution of points above and below the regression line surely seems like it's a problem here. So I've got just one dot here and several over here, whereas underneath the line, my main group of dots is in the middle. And that's a sign that I've got some kind of curve here rather than a line. So would a theory-based approach be appropriate? We probably feel like, no, not a great approach with this data. We'd be better off modeling it with a curve. I'm going to encourage you to pause the video and try this one out for yourself. So, would a theory-based approach be appropriate? Do we have points that follow a general linear trend? Well, they look like they're kind of scattered around, but around this line, I could draw myself an oval, and that's not too bad. So that seems to be okay. Do I have approximately the same distribution of points above and below? Got a big group of points here, mirrored by a big group of points there. So that seems to be okay as well. Do I have the variability being similar regardless of the value of the explanatory variable? In other words, as I travel along the line here, is this spread relatively consistent? And through the almost all of the data, it has a pretty consistent spread. We see a little bit of narrowing here, but these two are more outliers. Pretty much the bulk of data we see the consistent spread all the way through. So, and as I said, statisticians tend to want to say we've met these conditions. So even if we had a little bit of concern about these 2 points out here not really fitting in that great, we'd still probably say, yeah, we're okay. We can do a theory-based approach. And it might be worth pointing out that we had a couple of observations that are out at the high end there. I encourage you to pause the video and think of this one through. Okay, here would a theory-based approach be appropriate? Do they tend to follow the line? Yeah, we got a good linear trend there, so that's good. How about approximately the same distribution above and below? That seems pretty good as well. We got kind of just spread all the way along the line. There might be a little bit of an issue here where these guys here are don't really mirror this here that well, but that's actually more of a signal for this last one, which we do not meet. We definitely have some changing variability here. Data points are pretty tightly packed around the line. Out at this end, for our explanatory variable over to the right, much more spread, and it's kind of growing all the way. So we are seeing this trumpeting effect here. That problem there is a red flag for us, and using a theory-based regression approach here would probably not be appropriate. Out of the three things, if you have something that's not linear, that's definitely a problem. But then this is probably the biggest one to be concerned about. If we see this kind of trumpeting effect, it can really impact your theory-based approach results and make them not very valid results. There are some ways to deal with this. If you're interested in what do you do when you have a data set like this, I encourage you to think about taking one of our 200 level courses on inference and regression. And you can learn about different ways that statisticians deal with scenarios like that. But one that you already know, since we can't do a theory-based approach, we can do a simulation-based approach, and that would be a good option to choose here. I encourage you to pause the video and think this one through. So here, general pattern of points, do they follow a linear trend? Yeah, that seems pretty good. Do we have approximately the same distribution above and below the line? Well, you know, it's not the greatest, right? We got kind of a clump here that maybe is not quite mirrored by this here. We got just a few here and a few here. It's not awesome, but most statisticians would look at this and say, that's good enough for our purposes. We'd be okay. Part of the issue here is we don't have a lot of dots. This is a relatively small data set. So these gaps in here, we got to wonder if we collected more data, would we see some regular dots through here? Would it fill out like this? Or if we collected more data, would it somehow show more of like a curving pattern like this, which would be problematic? So small data sets can be hard to judge whether we've met validity conditions or not. And small data sets, I strongly encourage you to take a simulation-based approach, because there we don't have to worry about whether we met conditions or not. Lastly, variability of points around the regression line. So how spread out are they? And we've got kind of this amount of spread on this side and this amount over here. It's okay. Once again, fairly small data set makes it a little harder to judge these things, but most statisticians would look at this and say, yeah, we could do a theory-based approach in a scenario like this. So hopefully those examples are helping you understand how we can check validity and conditions. They're somewhat more interpretive in a regression setting, but it's still very important to look at a scatter plot and to get some sense of whether you're dealing with any of these problems or not. When all else fails, you can use a simulation-based approach and you don't have to worry about those conditions. But when we feel good about using a theory-based approach, then here are some of the details of what that implies. The parameter is the population slope beta, and our statistic is the slope from the linear regression equation, and that we symbolize with B in statistics. So y hat equals A plus BX, B is the slope. We have some theory-based approach formulas. I have one on the screen here for you to check out to calculate a t statistic. I don't expect you to calculate these by hand, but I want to show you that it's really the same formula we've used all along. And instead of doing these by hand, we're going to use technology. So we actually can calculate the t statistic from R, the correlation coefficient, with this formula here. We can also calculate it with the standard error of the slope. In other words, the spread, the standard deviation of the null distribution. And so this formula here is actually the exact same thing. And actually this one here as well. They're the same thing as what we've seen all along for a standardized statistic. They're our statistic minus the mean of the null distribution. Now on neither one is there minus anything, but that's because the mean of the null distribution in both of these cases is 0. So we typically don't write that. And then divided by the spread of the null distribution, and that's what those denominators are indicating. So it's the same formula. And if we get a standardized statistic with either of those formulas, we can interpret it the same way. It will tell us how far off our result was from the mean of the null distribution in terms of standard deviations. Here's an interesting thing to note. This t-test, the first one here, is based on the correlation, and it would give us the standardized statistic for a test of the correlation coefficient. It is exactly the same as the statistic we get for a test of the slope. They're mathematically equivalent, and they would give us the same p-value. What that means is if you're interested in doing a test of the slope, you could do a test of the correlation, and it would be mathematically equivalent. It would lead you to the same results. Some studies were interested in looking at the correlation. Others were more interested in looking at the slope. And so that's kind of how we pick which one we want, is which statistic is more interesting to us in this study. So as I mentioned, instead of using the formulas and doing that by hand, we're going to use technology, and specifically the correlation regression applet. We do not need to use any other applets. We can't use the theory-based inference applet for this. When we want to do a theory-based approach, we stick with the same applet correlation and regression that we've used all along. I'm just going to walk through the example with the same set of data we looked at in the last couple of videos. Here's some students, 20 students, lengths of their feet in centimeters and heights in inches. And we look at a scatter plot, and the first thing to do is to assess our validity conditions to see if we can use a theory-based approach. Does it look reasonably linear? Yeah, it looks reasonably linear, right? We could get our line going through here. In fact, I'll show it here. And that looks like it's reasonable to follow the line. Do we look like we have at least roughly symmetrical distributions above and below the line? So yeah, my points are kind of scattered all around over above the line and below the line. So that looks okay. Once again, it's a small set of data, so don't read too much into kind of some of the dips and sways here. Just the general scattering seems similar above and below. And then thirdly, do we have any kind of trumpeting or fluting effect where it's really shrinking down or growing big? And here I'd say if we, especially if we ignore this one kind of popping out here, I'd say we have, looks like a pretty even spread all the way around, along the line. A couple that fall outside of that, but nothing that's too much of a red flag for us here. So, so we can use a theory-based approach here. This should be good. How do we do a theory-based approach? Well, first thing is to calculate the regression line and find our statistic. And so here it is, regression line, height, approximate height equals 38.3 plus 1.03 times the foot length. And here's our slope of interest, 1.03. To do the theory-based approach, all you have to do here is simply click on the regression table check mark, and it brings up the results from a theory-based approach. So we get two rows in this table besides the headers here. The top one is the intercept. That's the row for inference with the y-intercept. And you can see it gives us the y-intercept value here. We're almost never interested in this test. This is a test to see whether our intercept is significantly different from 0. And here, it doesn't even make sense to think about the y-intercept. It says, this is how tall someone should be who has feet that are 0 long. So it's not a very meaningful thing, and we almost always just ignore this row in the table. There are a few instances where the intercept is what's interesting to us, but for the most part, we're interested in the slope, which that's the term in our equation with foot length in it. That's this term, and the coefficient in this term is the 1.03, and that's the slope number. It gives us the SE, the standard error. That's the spread of the null distribution. And then here it gives us the t statistic and a p-value. We can evaluate either one of those. T statistic, our result is 4.29 standard deviations above the null claim of a slope of 0. That's a long ways above. 4/4 standard deviations, that's crazy to be that far away from 0. We see that reflected in the p-value. There's almost no chance, a 0.04% chance, of finding a result like a slope of 1.03 if the null hypothesis is actually true, if the real slope in the population is 0. We'd almost never find a result like this. Therefore, we can reject the null hypothesis. We don't think it's true that the population slope is 0. Instead, we feel like the slope is higher than 0 in the population. There is some kind of association between foot length and height. And we've looked at this data a couple of times, so we're not too surprised to find that. In addition to the test of significance, we can find a 95% confidence interval. Note that before you open up the table, that's not even available to look at. So you got to click on that first. Then you can click on 95% confidence interval. Here we go. We feel 95% confident that the true slope in the population is in between 0.52 and 1.53. So what's that saying? We feel 95% confident that the increase in height on average is somewhere between 0.52 and 1.5 for every increase of 1 centimeter in your foot length. We can talk a little bit about a meaningful difference from 0. Does that seem like it's meaningfully different from 0? Well, it seems like, I mean, this is kind of an interpretation here, but let's look at the low end. That's a 1/2 inch. we're saying the trend is that people would be in half an inch taller for every centimeter of foot length. And that seems like it might be a meaningful thing, right? If their feet were big enough to notice a difference, that'd probably be at least a few centimeters. They'd end up being, a few of these half inches taller, which people would probably tend to notice. So I'd say, yeah, it seems like there's a meaningful difference from zero here. Couple last quick comments. Who should these results apply to? Well, we haven't said much all along about who these 20 people are. So it's really hard to say without knowing how this sample was gathered, who these results should even apply to. A much better study would make it clear who these 20 are. Maybe they're a random sample of students at a college or something like that. So we have a big weakness on generalizability there. Finally, can we conclude cause and effect? Does having bigger feet cause you to be a taller height? In order to conclude that, we would have to have people randomly assigned different foot lengths for this study. And of course, you can't randomly assign people to have certain length feet. So there's no way to claim cause and effect here from the study that we have set up. So that's how we can do a theory-based inference with two quantitative variables and looking at the slope of the regression line.